Hi, hello, and good day to everyone. Today I'm going to present about the Seakeeping project for the dynamic of marine structure. My name is Arvinthan, son of Thiagarajan, and my group members' names are Tafiq Islam, Haifaa Zira, and Nick Mohammed Hafiz. I'm going to present about our project. So the content of the project is introduction, ship simulation software, seakeeping performance of a small fishing vessel, result discussion, conclusion, and reference. Now we're going to see about the introduction. David M. Bowie on 1973 make a study on the server ship roll motion. He also developed a time domain simulation program for the ship capsizing for in a following wave. In that study, it examined the low cycle roll resonance in the force half motion and American Challenger. Examine effects of variation in the ship characteristic, initial condition and wave conditions are capsizing tendency. And then he also highlighted that the potential of capsizing before the crew awareness. Next, we're going to see about the Bovet wave phenomenon. The figure shows that with the in a ship in the wave with crest emission, the transverse inertia is lost at both ends without any gain amidship. The transverse inertia increases when the wave crest and the passes amidship. The stability fluctuates with the transverse metacenter's position change over the time. Next, we're going to see about the vessel's transverse stability variation and its effects. The vessel transverse stability can be affected by the periodic variation due to the regular wave encounters. The frequency of the stability variation doubles the natural roll frequency. The high stability value and a quick recovery to upright position are observed. The wave crest weaken stability allow for the heavy roll due to the roll on other side. Wave through the amidship position increase the stability at the top of the roll. The ship rapidly rights itself and roll heavily against the less stable wave twist amidship. That's it for the introduction. My friend will be continuing.
Hello, Assalamu alaikum. Basically, because we have to simulate our the data to get the lead roll, pitch, and different parameters. We need to do some iteration, and to do some iteration, I think a simulation software will be very helpful. So in our case, we have used photon coding, and the vessel, as our previous group member has already mentioned, will be the American Challenger. So now you can see from the slide there are some parameters which is based on the vessel. There are some parameters here which we should used for the input of the simulation. Okay, moving on to the next slide. Now, from the input parameters, we have also get the offset value. So basically, the offset value shows us that the cross section of the whole vessel from the aft to bow section, separating from 0 to 10 station, and there is the depiction of that offset data according to the value given. So next up is how do we run the first our first program. So basically, as we have already found or prepared the input data for the vessel, now we need to prepare the executable source code. In our case, we have prepared the mom.for, that is for the photon source code, and we have used the methodology to get the sorry uh, section area and sectional transverse writing moment and we have used the methodology given in the RMOMT program. So using this methodology, we have found the MOM underscore UT output. So basically, we have to execute the Fortran code, and we get the output. We get our output result. Moving on to the next slide. So this is our result for the first simulation, and from the figure 2.2 we can see that section area at various hills and depths of immersion, and for figure 3 it has been depicted that writing moment at various hills and depths of immersion. Okay, now that we have completed our first simulation, we have to do our final simulation, that is for running that is with running the ship.for code. So basically, as we have already prepared our MOM-UT output data, in this case we have to use it as an input data, and then we have to run it through Fortran code, and then we get our output result. Excuse me. As you can see from the figure 2.4, that is our input file, and there is a 6th line. So moving on to the next slide, I can describe it further. This is for the line 1. This line 1 is basically based on the input data, or here in this case the output data. Line 2, similar to the previous one. Moving on to the next slide, line 3, same. Line 4 and line 5. Line 6, this one is line 6. So all of the input data has been defined here, so that no one will face any problem when configuring anything in the future. Now that we have done our input data and prepared our Fortran code, we are ready to derive our result. In this case, we have gained or managed to present the data for heap, pitch, roll, moment, roll, wave, and metacentric height, and the horizontal metacentric height based parameter. Now this is our one of the most desired figure. In this case you can see that heap and pitch, and for figure 2.6 you can see the wave and roll parameters. From these two figures everyone can assume the ship stability or something like that, and so that anyone on the board will not face any problem when seakeeping on maneuvering the ship. So I think from this figure it will be very helpful for the future case as well. And one more thing I want to add, that there is a phase difference between heave and pitch. It has been clearly seen from the figure. Okay, now this one is a moment, and also the metacentric height based parameter. So this figure, I think all of the previous figure, I think will be our main target to keep our vessel or as well as ship to make it stable enough to perform in the real environment. Now our final content is basically actually my final content is basically to show you that the document flow of our work. So we have to first think of our work, that how we are going to run the program, and then we prepared the our vessel parameter. Then we have, after that we have run the our first simulation through the Fortran code. Then we get the output result, and from that output result we have made it as an input for the next program. I mean the ship program. Then running the ship program, we get the different parameters. That is our different desired parameters for the depiction of our ship stability in future case. So that is how we are gonna make this program run.
Assalamualaikum and good day to all of you. My name is Haifaa Zira. Today I will continue on the seakeeping performance of a small fishing vessel. Seakeeping performance of a small fishing vessel refers to a vessel response to wave, crucial for operational safety and effectiveness. The objective of this assessment to investigate the seakeeping performance of a small fishing vessel in sea state 3 conditions following the methodology of David and Bovert 1973. Offset data is essential for accurate vessel modeling, which is the fishing vessel's data required enhancements to correct position errors and redundancies. MOM1 program was utilized to process the enhanced offset data and generate the body plan for the fishing vessels. And this is the fishing vessel's body plan that consists of 11 sections. This is important to provide a visual representation of the vessel geometry for simulation purposes. And this is for the fishing vessel specification that consists of LBP, lowest and highest draft, draft increment step, lowest and highest heel angle, heel increment step, station spacing, design draft, and also ship name. The parameters containing draft range, heel angle range, LBP, and station spacing is set for the MOM1 file as shown in the snipping boxes here. The section areas and writing moment for station 0 at 0 degree of heel and 15 draft steps from negative 1.127 meter to 2.127 meter as shown here. Then, the ship file contains the ship and wave parameters for the execution of ship 4 file. The parameters are established with reference to American Challenger parameters, geometries of the fishing vessels as well as the sea state 3 condition. 12 scenarios has been proposed to represent the variation in ship characteristics, initial conditions, and wave conditions. The parameters for ship file of all scenarios with the maximum program runtime of 100 seconds as shown in this table. That's all for my part. Thank you.
Assalamualaikum and good day. I'm Hafidz, and today I'm going to present about result and discussion. The output of the program for ship capsizing simulation are shown in form of roll motion graph at different initial draft, ship speed, and initial position of wave crest, up, or forward perpendicular, or EPS. Figure 4-1 shows that the vessel experienced the worst condition and it capsized earlier at EPS equal to lambda over 4 or 3.1825 meter during service speed for both initial draft. The ship improved the capsize time at lower initial draft during stationary condition, but showed opposite pattern for service speed condition. As EPS equal lambda over 2 or 6.365 meters, the ship capsized quicker during stationary and higher condition, but it has better response at lower draft during service speed condition. Based on the worst condition at EPS equal to lambda over 4, for both draft at service speed, heavier vessel, which is high draft, has better roll response, but the ship operator need to justify why the selection of the speed, as the vessel tends to capsize quicker at higher speed. Nevertheless, the ship shows the same pattern during EPS equal to 0 and lambda over 4 with variation of draft, but with the same state speed. The following figure 4-2 till figure 4-9 show the increasing magnitude of roll and GM values before the ship capsized due to excessive roll motion. For scenario 1, 2, and 3, as shown in the figure 4-2, at stationary ship condition, the ship tends to capsize faster at EPS equal to lambda over 2, but will capsize slower as EPS equal to lambda over 4. For scenario 4, 5, and 6, which is at the surface speed condition, the ship tends to capsize faster at EPS equal to lambda over 4, but will capsize slower as EPS equal to 0. Then the simulation is conducted at lower draft of 0.7 meter, which is we can see in the scenario 7, 8, and 9. At stationary ship condition, the ship tends to capsize faster at EPS equal to 0, but it will capsize lower as EPS equal to lambda over 2. It shows different pattern in comparison with higher initial draft of 0.8, but with same speed value of 0 knot. At service speed condition, the ship tends to capsize faster at EPS equal to lambda over 4, but will capsize slower as EPS equal to lambda over 2. It shows same pattern as EPS equal to lambda over 4, but at higher draft of 0.8 meter. And roll motion from figure 4-10 show the low cycle roll resonance phenomenon. The vessel has a high stability value and quickly recovers to the upright position. A heavy roll is now possible as the vessel rolls to the other side due to the wave crest weakened stability. Once more, a wave roll moving into the amidship position is the reason of the greater stability at the top of its wave. As a result, the ship rapidly rights itself and rolls heavily to the opposite side in the opposition to the wave crest amidship. That is causing less stability. This process goes on for a number of wave encounter cycles under a normal wave condition, increasing the roll angle until capsizing eventually happens at 19.5 seconds. In conclusion, the seakeeping characteristic of the fishing vessel can be predicted for the range of EPS equal to 0 till lambda over 4. The ship is prone to capsize at higher speed, and the initial position of wave crest or EPS equal to lambda over 4. The analysis also shows that there are possibility of ship capsizing for the vessel even for the slight characteristic of sea state 3 in following the condition. As for the recommendation, further research is recommended to explore additional scenario and vessel types, as well as to refine simulation model to even more accurate prediction of seakeeping performance.